Welcome to this lesson on techniques for computing limits. Today, we'll explore various methods for calculating limits, including infinite limits and limits at infinity. Let's begin by discussing some basic techniques for computing limits. The first technique is direct substitution. If f is a continuous function at a, then the limit of f of x as x approaches a equals f of a. This is the simplest approach. Just plug in the value and evaluate. The second technique is factoring and canceling. When direct substitution gives us an indeterminate form like 0 over 0, we can often factor the numerator and denominator to cancel common terms. The third technique is rationalizing or conjugate multiplication. This is especially useful for expressions involving square roots. We multiply both numerator and denominator by a conjugate expression to eliminate the radicals. The fourth technique is combining into a single fraction. When dealing with sums or differences of fractions, combining them under a common denominator can often simplify the calculation. Finally, we have L'Hopital's rule, a more advanced technique. If the limit of f of x divided by g of x as x approaches gives us an indeterminate form like 0 over 0 or infinity over infinity, then this limit equals the limit of f prime of x divided by g prime of x as x approaches a, provided the latter limit exists. Now let's move on to infinite limits, which occur when x approaches a finite value, but the function grows without bound. An infinite limit occurs when x approaches a finite value a, but the function value increases or decreases without bound. This typically happens when the denominator approaches 0 while the numerator remains non-zero, creating what we call a vertical asymptote. Let's look at an example. The limit of 1 divided by the quantity x minus 2 squared as x approaches 2. First, let's check what happens with direct substitution. If we plug in x equals 2, we get 1 divided by 0 squared, which is undefined. The denominator is approaching 0, while the numerator remains at 1, so we expect the limit to be plus or minus infinity. Next, let's do a sign analysis. The expression x minus 2 squared is always positive except at x equals 2, where it's 0. So for x near 2, the denominator is positive, making the entire fraction positive. As the denominator approaches 0, the fraction grows without bound in the positive direction. Therefore, the limit of 1 divided by the quantity x minus 2 squared as x approaches 2 equals positive infinity. Now, let's discuss limits at infinity, which occur when x approaches plus or minus infinity. When x approaches infinity, we often need to analyze the behavior of functions with large input values. For rational functions, we compare the degrees of the numerator and denominator to determine the behavior as x grows very large. Let's look at an example. The limit of the fraction 3x cubed minus x plus 2 divided by 5x squared plus 7 as x approaches infinity. Step 1. Divide both numerator and denominator by the highest power of x. In this case, the highest power in the numerator is x cubed, so we divide everything by x cubed. This gives us 3 minus 1 over x squared plus 2 over x cubed in the numerator, divided by 5 over x plus 7 over x cubed in the denominator. Step 2. As x approaches infinity, all terms with x in the denominator approach 0. So, our expression simplifies to 3 divided by 0. Since 5 over x is positive for large x, the denominator approaches 0 from the positive side, making the whole fraction approach positive infinity. Therefore, the limit equals positive infinity. For rational functions, we can use a degree comparison rule to quickly determine the behavior at infinity. If the degree of the numerator is less than the degree of the denominator, the limit at infinity equals 0. If the degrees are equal, the limit equals the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, the limit is plus or minus infinity, with the sign depending on the leading terms. Now, let's look at some more examples of using the techniques we've learned. Example 4.1. Let's find the limit of x squared minus 1 divided by x minus 1 as x approaches 1. If we try direct substitution, we get 0 over 0, which is indeterminate. So, let's try factoring the numerator. We know that x squared minus 1 equals x minus 1 times x plus 1. This gives us x minus 1 times x plus 1 divided by x minus 1, which simplifies to x plus 1 for x not equal to 1. Now we can substitute x equals 1. The limit equals 1 plus 1, which is 2. Example 4.2. Let's find the limit of the square root of x minus 2 divided by x minus 4 as x approaches 4. If we try direct substitution, we get 0 over 0, which is indeterminate. So, let's try rationalizing the numerator. We multiply both numerator and denominator by the conjugate, which is square root of x plus 2. This gives us the quantity square root of x minus 2 times square root of x plus 2, divided by the quantity x minus 4 times square root of x plus 2. The numerator simplifies to x minus 4, which cancels with the denominator, leaving us with 1 over square root of x plus 2. Now, we can substitute x equals 4. The limit equals 1 over the quantity square root of 4 plus 2, which is 1 over 4, or 1/4. To summarize what we've learned about computing limits, first, try direct substitution. If the function is continuous at the point, this will work. If you get an indeterminate form like 0 over 0, try algebraic techniques such as factoring, rationalizing, or combining fractions to cancel the 0. For limits that blow up at a finite point, perform a sign analysis to determine whether the limit is positive or negative infinity. For limits as x approaches infinity, use the degree comparison rule for rational functions, or divide both numerator and denominator by the highest power of x. And when all else fails, consider using L'Hopital-Less rule for appropriate differentiable forms. With these techniques, you'll be able to solve most standard limit problems you encounter. Thank you for watching this tutorial on techniques for computing limits. With practice, these methods will become second nature, and you'll be able to evaluate complex limits with confidence.